on this computer. I am screen sharing. Great. So people on Zoom can totally see this. So today, what we're going to go over is our first exposure to for loops. If you already know Python, this one is going to be a bit boring. Sorry. If you're coming from a different programming language, this will be very valuable, because if you haven't noticed from Tuesday's lecture, the for loop feels very different. And if you're completely new to programming, this is going to be extremely valuable because you haven't done this before. So for loops, so the three components of basically imperative programming are, you have imperative statements, conditional, and iterative statements. I suppose you could say they're conditional statements as well. I mean, there's probably a formal syntax for it, but but basically what it comes down, but the way you always remember it is that you've got your if statements, which are commands like x is equal to 5, print x. Those are each an imperative statement. Imperative as in imperial, as in command, So they're just basically, doing the imperative statements means you actually do something. A conditional statement is something we'll learn later, but they're very useful. They're basically if-else choices. And we'll see that they look something like this. If x is greater than 3, then we do something. I'm going to go ahead and print Bing, else print Bong, because changing up vowels like that is fun and nonsensical. So let's see. So basically, we say x is greater than 5, print x. If x is greater than 3, we print Bing. Otherwise, we print Bong. That's what the if-else statements means. We do not have to worry about this today. I'm just mentioning this for completion's sake. This is what a conditional statement is. Okay. Finally, we have our iterative statement, which is what we're going to be focusing on today. Iterative statements can be while loops, which we'll talk about later. They're while loops. While condition is true, do the following. All right, while x is greater than or equal to 5, we want to do something. Print, but don't fill that in, because guess what? It's going to be an infinite loop there if we don't change x. So we're going to just simply ignore that for now, but know that the while statement exists. We'll teach it much later. It's not even going to be on the first. I don't think it will even be on the first exam. For loops will be. If statements, probably, maybe, kind of, but definitely for loops and turtles. For loops and turtles are like the focus of my first exam. Okay. So let's see. We've got our imperative statements. We've got our conditional statements. Finally, we have as I've mentioned, the iterative, we have while statements, and we have the for loop, which we talked about yesterday, or sorry, not Tuesday, which basically we said looked like this: for blank in range some number. So I'm going to say 3 and print this is repeated 3 times. Right? And what that does, so for loops are useful for that. Basically repeating things. And again, this is going to be the focus of today's lecture. So let me go ahead and comment these things out, because you probably were taking notes. That's fine. But, this is the equivalent of me, erasing the whiteboard, only not nearly as bad. Okay. So the idea here is that I want to focus on these for loops. Now, for loops are used for basically 3 different purposes that we'll see in Python. So it's repetition without change, repetition with minor change and iterating over a structure, which is very abstract terminology there. Iterating over a structure, what in the world do I mean? So repetition without change is the thing we've been looking at. So again, if I say we have some value num is equal to 3. So let me go ahead and rewrite what the for loop I just wrote, just to make it a bit slightly more abstract than last time. For in range num, so num is equal to 3, so this value is going to be 3. Print this statement prints, and you'll forgive my spelling, this statement prints num times. And when I do that with the print statement, it prints 3 times because I had 3 for number. And so it prints out that it prints out 3 times. If I changed it to 5, it would do so. And if I changed it, and you don't want to do this to your computer necessarily, but if I did do this for 100,000, it would attempt to do so 100,000. And in fact, it would do so until I got bored and told it to stop, which you can do by hitting Control-C or Command-C, or just going to shell over here and hitting interrupt execution, which will hopefully crash your program, but sometimes not. In which case, we can just simply kill that like that. You'll run into I guarantee you when you're coding, you're going to run into a circumstance where it just keeps repeating, and you'll just need to manually kill it. It happens to everybody. It's annoying. You just don't want that to happen for your final submission of an assignment. That's all. But this is basically repeating something without change. The idea here is that we use a for loop to repeat something, to do the same command over and over again without any variation. A good example of this is when we were messing with our turtle and drawing the shapes. To draw a shape, we wanted to make the same exact line and turn, a certain number of times. So if we wanted to do an octagon, we wanted to make the same turn and stroke 8 times. No changes. Iterate. This is something we're not going to go over too much today because it's fairly straightforward. It's you've got a statement in here. You may have multiple statements in here, but they're each going to repeat, a certain number of times. So if I turn this back to 3 and say print, whoops, yay caps lock, print this one too, both of these will print out num number of times. Whoops, now 35, I guess. So because I hit the wrong button. Oh well, 35 is manageable. So we've got that. So go over here, and you can see that each of these statements now print out 3 times. Again, this isn't too exciting or complicated. Iterating over a structure, I suppose the term we should use is sequence, because I think of it in terms of data structure, but they use the term sequence in our textbook. So any kind of sequence means things that are in order or things that are collected together. So we're talking, and we've already been working with one, which is like a string. And that looks like this. So say I have some text is equal to why hello there. Okay. So then if I go ahead, and so I can write a for loop that looks something like this. And this is known in other programming languages as the for each loop. Python only has the for each loop. That's all we have. But in other languages, this is like a secondary loop. It's not the first one you typically learn. For letter in text, print letter. And once we see what this does, it makes a ton of sense. It prints out why hello there, but vertically, Can print out, in fact, what it's doing is printing each letter in the loop, not just each letter, but each character in the loop, right? Do I need to increase the font size, or is everybody cool? Okay. So this variable letter could be anything. It could be foo, which is a classic metasyntactic variable. Metasyntactic variable meaning the name of variables that we use to make up fake variables. It actually differs from languages. The metasyntactic variables in English are in American English are typically foo, bar, and baz, relating probably to the commingling of early computer science with the Army, because FUBAR is a very popular acronym from the Army. It means something like fouled up beyond all repair, something like that. Okay, so anyway, so this could be anything, but basically it's saying for each individual item in the thing that can be broken up into individual items, right? Text can be broken up into individual letters. A string can be broken up into individual characters. If, on the other hand, I said big number is equal to, 1,000, or let's say 1, 2, 3, 4, you might expect it to go, and if I were to do this for foo in big number, your first instinct would be maybe it does do like 1, 2, 3, 4, but it will tell me that it will give me this error. Int object is not iterable, meaning that you can't use a for loop on it. That's what it's saying. It's not an iterable. If it's iterable, you can use a for loop on it. And saying that you can't iterate over this number because how am I supposed to iterate over it? It's ambiguous. Do you want me to go over the digits? If so, do you want me to go from left to right or right to left? Do you want me to go from hundreds, from the big place, or from the ones place and up? I wouldn't know. Or do you want me to count up to that number like you do in range? So there's ambiguity there. Whereas in text, there's no ambiguity. You probably just want to go from the first to last. That makes sense. But here, this is not iterable. We don't know how to break it up into things. And it's a number. It's not really made up into stuff. Also, that's not the number that the computer sees. It sees a bunch of zeros and ones to represent a number. Whereas each of these is a sequence of zeros and ones. Each letter is a sequence of zeros and ones that is all just simply glued together. Yes. Yep, because then it would be text. That's a great question. This will work because now it is text. But the point being is that we can iterate over text. This will be very useful later on. But again, I'm just simply including this here for completion. Today's focus is on change with minor repetition. And again, you're going to be introduced to the for loop. You haven't even seen it in the textbook. Why am I bothering going over this? Because the for loop is something that trips up most freshman computer scientists in their early class. That's why. It is the first hurdle mentally in this. And so I try to introduce it multiple times as though it's the first time you're being exposed to it. This is why I'm introducing it to you in class before you see it in the textbook, before you even have your exercises. You can use for loops in lab 3, but you don't need to use for loops in lab 3. All lab 3 requires is turtles, doesn't require any for loops. Lab 4 and 5 require for loops and turtles, and lab 4 and 5 is one big lab. It covers both lab 4 and lab 5. Make sense? Okay, so repetition with change. So you notice that over here I had something like for foo in text, but over here I had for blank in range. And I mentioned something is that you could put anything there. Doesn't really matter for this statement, right? I can put anything in here. You use blank when you say I don't care what it is, but I could do something like for I in range, and it's not going to change anything. Oh, I have to declare the num over here. I didn't declare that. That's why that crashed. So here, right, I changed the blank to I. That's all that's different. I changed the blank to I. Go ahead and actually make that a bit easier for you to read and kind of a note sense of the word. Okay. There we go. And so now let's go ahead and try experimenting by printing out I. We print out I. So if we say num is equal to 3, we print out and we say for I in range over number, print I, we get 0, 1, 2. Let me go ahead and make it a bit less abstract. If I replace this by 5, and I say for I in range 5, it prints out the numbers 0, 1, 2, 3, 4. If I say range to 10, it's going to print out all the way to 10. If I tell it to, it will go up to, but not include 10. It'll go, and if I do 100, it'll go 0 to 99. What range? I took out my pen yesterday and didn't put it back in. What range does in mathematical terms is that it creates a range of numbers for Python to iterate over, right? It's really just doing this, but it's this third case, but it's disguising it. What it's doing is that it's creating a range of numbers for it to iterate over. And in mathematical terms, it's basically going from 0 to the endpoint. But it's written like this, if you remember your graph notation at all, which simply says we start at 0 and we go up to, but don't include the end, right? The square bracket is used for inclusiveness, right? And the closing parenthesis is used to say we don't go up to the end. So for instance, if it's 0 to, if we say if our ending point is equal to 100, if this is equal to 100, that means that we go all the numbers from 0 to up to, but not including 100. That means 99. And when I mean number, I really mean positive integers here, or integers, because 0 technically isn't positive. But the point being is that we exclude 100. Now, why is this why in the world did we decide that if we say for I in range 100, okay, you can understand the starting at 0, okay, maybe. But why do we go up all the way up to 100 and not include it? And the answer is because we can figure out how big this range is very simply if we use this includes excludes notation, which we'll be messing around with a bit later. Okay. If I say, if this is 0 up to, but not including 5, I know that this is 5 long because I can take the end. So I can take the start and subtract it from the end. 5 minus 0 is 5. So it's 5 so it's 5 items long. There's 5 numbers in the sequence 0, 1, 2, 3, 4. Okay. Which implies that we could start at a number other than 0. I could do 1 up to, but not including 5s. 5 minus 1 would be 4. So there'd be 4 numbers in that range. And in fact, you can do that in Python. We can do something like that. We can say 1, 5. This is the other way to do it, which is you can be explicit about your start and end points in the range. So we can create ranges of numbers like this. 1 to 5, we could do 10 to 20, which would be 10 numbers long because subtract the start from the end. 10 minus 20, it will go 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 10 numbers, right? And again, I don't know what it is, but the more advanced mathematics you get, the harder that the basic stuff gets. So there you go, 10 numbers. Now, what if you want, it's pretty cool. Now, what if you wanted to go 20 to, what if we wanted to start at 20 and go to 10 though? It's gonna not really do anything because you can't count up from 20 and go to 10. We have one more comma we can put in, which is the step, saying how you'd like to go from one number to the other. By default, it assumes you want to count up by 1. By default, any sequence is this. But what we want to do is count down. So we would put -1 there. And then we can do 20 down 2, but not including 10. Same principle applies. Start at 20, go down 2, but don't include 10. This is useful for, this is kind of useful, and you'll learn more about it later. But we can also, but on the positive end of things, we can do things like this. I want to go from 0 to 100 up by 5s. And now I can count up by 5s, which would be less impressive. Oh, sorry, which would be more impressive if my kindergartner couldn't do it, I guess. So, you know, he can count up by 5s. He's very proud. All right, so why am I talking about this? Well, because today I want to talk about one of those values that we were discussing yesterday, which was this one, or if I can actually draw it, pi. Pi's value is 3.14159, and it is the ratio of the what? So it is what, 2 pi r is the circumference, so it's the ratio of the, it explains the ratio, it defines the ratio between the diameter of a circle and its circumference. If that doesn't make sense to you, then again, let me show you Wikipedia. Because again, Wikipedia is great. You know, it's not because of all the text that people just drop in, but because they have these beautiful animations. Here's a circle, a unit circle, and they line it up. And what they show is that basically this thing is 4 circles long. The diameter of each of these circles is 1. And if we unroll those circles, it will unroll up to 3.114. That's what it means by the ratio between the diameter and the circumference. You get, given 1 diameter, you get pi circumference. Okay, so it's a bit more than 3. So the question is, how in the world do we get 3.14159? And oh, it's an irrational number, of course. So that means that there's no fraction that perfectly defines it, which means that we have no idea, which means that it kind of just goes on forever and ever and ever and ever. You know, as you can see, it just simply goes on. It's got a repeating pattern, and it's like a flex to be able to memorize more digits in some circles. I mean, cool. I mean, you got to have something to occupy your time. So anyway, how in the world do you figure this thing out? Well, and it mentions here that there were ancient civilizations used, they needed to build their things, they needed to have fairly accurate approximations of pi. And so if we look on Wikipedia for approximations of pi, hey, it's almost as though I've searched for this before. We can see that as the years have gone up, the amount of digits we've been able to figure out for pi basically took a huge skyrocket once computing came into the forefront. Okay, so what did they do beforehand? Well, Archimedes, he drew polygons to figure it out. And he used he kind of drew polygons and rather than making a circle, he did what we did, which is that he made something that looked like a circle, a 96agon, to be able to kind of estimate that pi was somewhere between, not estimate, but to solve that pi sat between these two weird fractions, 22/7 and 223/71. Let's see. So there's been a number of Chinese mathematicians who calculated pi through different fractions. They said that pi was approximately equal to this fraction. Zhu Chongqi gave this approximation that I really like, which is 3, because it's not too bad to remember. It's 355/113. And if we plug that into our interpreter, 355/113, let's see, why in the world is that there? Is there something wrong with my shell at the moment? There we go. Oh, it's probably some, I don't know what happened there. Oh, well. 355/113. over 113. $355. Ugh. 355, 113. And you see that it comes out to 3.1415929, which that's pretty accurate, because what we're talking about with pi, again, is pi's digits are 3.1415926. So it got all the way up. So that fraction gets you all the way here. Sorry, all the way through here accurately, which is pretty darn good. But I mean, other than testing fractions, how in the world do we get there? Well, formulas. Lots of fun looking formulas like this guy. One of my personal favorites is, and the one we'll be discussing today, let's see, is this one over here. The Madhava Leibniz series. It used to be known as Leibniz series, but then it was shown that, hey, that Indian mathematician had come up with it quite much earlier. There's been a number of these kind of renamings in mathematics, because Euler got named after pretty much everything because he discovered a lot of stuff, but also a lot of other people did. So the Madhava Leibniz series, and what it is that we've got this basically this alternating series of fractions: 1 minus a third plus 1/5 minus 1/7 plus a ninth minus dot 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 all the way to infinity. If we keep adding these if we keep on, the more and more numbers we add to this, the more longer we continue this pattern, the closer it gets to pi over 4. Okay, pi, and so again, pi over 4, that would be, so let's see, approximately, no, import math dot pi as it's stored in there. So math dot pi divide by 4. So approximately 0.785. Okay, bit more than 3/4. Okay, so the more and more numbers we add, the closer we're going to get to pi over 4. Multiply that value by 4, you get pi, or something close to it. It can be related to other things, and there's proofs for it, which we don't need to cover because that requires calculus. And it slowly converges to getting to the 3.14. So what we're going to do is that we're going to compute this using for loops, using one of the most common tools we'll have in when using a for loop, called the accumulator pattern. Basically, that we're going to add values together and we're going to store the running sum in a variable. So for instance, what do I mean by that? So let's see. Let's go ahead and comment all this out and start up over here. So let's talk about running the accumulator pattern. Over here, we have some amount, we use some variable as the total. We typically start it at 0 because we're going to be adding things to it. And if we had anything other than 0, that would change the values that we'd be adding to it. Okay. And what we do is that with this accumulator pattern, is we do something like this. For I in range, well, let's start out simple. Let's just do the same thing over and over again, rather than slowly changing it. For I in range 5, what we're going to do is that we're going to, each time the statement runs, we're going to say total is equal to total plus 5. All right. And then print total. Sorry, I have it from Python point. You used to be able to do print space rather than parentheses in Python 2, but they changed that in Python 3. 25. How in the world do we get there from here? Well, the answer is imagine that total over here is a box, okay? this statement repeats 5 times. The first time we set up total is equal to 0 for blank and range 5. So this is going to repeat 5 times. Total plus equals, sorry, total is equal to total plus 5. So it says figure out what's in total, which is 0, add 5 to it. That's 5. Okay, what does that equal to? That's 5. Okay, take that value and store it in total. So we do that for our first, so after our first operation is done, we store 5 in total. That's our first time through the loop. Now we go through our loop again. Okay, we say total is equal to the value. We see this total over here, and what we're saying is inside this, please store the sum of total plus 5. What is total? That's a variable. Look it up. Okay, I'm going to check inside the box. It says it's a 5. Okay, 5 plus what? 5. Okay, 5 plus 5 is equal to 10. Now store that inside the box. And so the box becomes 10 after the second time. Then it's quite easy to see that's going to become 15 after the third time. I'm not gonna, bore you to death by doing it all 5 times. As you can see, it keeps adjusting this. It keeps adding 5 to it. Now, where the hard change comes in for a lot of students is this. Because now we have to keep track of 2 variables. Well, now we have to keep track of 2 variables. So this is equal to 10. How did we get there? Well, going back to our drawing, we have our drawing of total, but we also have over here I. So for I, so in our first time, so remember, this is going over range of 5, which is the value 0, 1, 2, 3, and 4. So our first time through the loop, I is equal to 0, total is equal to 0. So we add, so it's asking, okay, 0 is equal to 0 plus 0. Done. Okay, now let's go to the next value in the range. That's I is equal to 1 now. Okay. Total is equal to 0 plus 1. Okay, that's equal to 1. Go ahead and store that in total, which we do. Now let's go ahead and erase so that we get 2. So let's clean up a bit. One. Now we update, so we finished adding 1. Then we add 2. 2 plus 1 is 3, so we store 3 in here. Then I becomes 3. We add 3 to we take we take the 3, add it to the 3 in total. That's equal to 6. So we store it in total. And then finally, for the last value, I is equal to 4. So we would take 6 plus 4, store that in total. Total is now 10. That's how we end up with 10. In other words, what I've done is just simply add up all these numbers together. 1 plus 2 plus 3 plus 4 is equal to 10. This is called an accumulator pattern. We just simply add more and more things to it individually. Okay. So, but this is like, however, if I were to say, okay, so now please go and do this, that would be kind of cruel. It's like saying, it's one of those classic things of like, this exercise is now left to the student. Except it's way more complicated because there's a couple of different things going on here in this, right? We have an accumulator. It's this pi over 4 value that's going to hold pi over 4. But what we're doing is that we're starting at 1 and then we're adding fractions. Okay, that's weird, except we're not just adding. Notice that it's an alternating sum. Minus, plus, minus, plus, minus, plus. Okay, so we have to go around, we have to handle that in some way. And the way you take, and so this is a fairly big problem. Big in the sense that we have there's a lot to it. and it's too hard to do all at once with just having learned this. But the key thing you do in computer science and programming in general is that when you have a problem, you break it down into easier steps. Say, I'm going to solve each of these when I get the chance. So first and foremost, let's figure out that plus and minus alteration later. Right now, I'm just going to work on adding up all the fractions. Going to add them up. We're going to work on figuring out the subtraction later. Furthermore, I'm going to worry about this nonsense about the 1 over later. Right now, I want to work on 1 plus 3 plus 5 plus 7 plus 9. Make sense? That's totally not what the question asked for. It's not going to get us pi over 4, anything we are close to it. But we need to get this pattern going, right? We need to get this pattern going. And not only that, but doing this kind of addition, it's easy to check our answer. It's much harder to check mentally what's 1 plus a third plus 1/5. I don't know, that's hard. It's like 1.5333333. You get the idea. And God help us when we add the 7th and the 9th. Okay. So fortunately, I did just explain kind of how we can do this pattern of adding 1 plus 1 over 2 plus 1 over 5. Well, not 1 plus 1 over 2, but 1 plus, it was 1 over 3 plus 1 over 5. Or more specifically, I explained how to do the 1 plus the 3 plus the 5 plus the 7, right? We can, with the for loop, we have control over how we want to go up, right? We have control over how we want to go up. We can say, I want to go from 0 to 100 up by 5s, right? So I can say I can go from 0 to some other number up by however many I want. So let's go ahead and start by rewriting this all. Boom, 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 boom. Okay, so let's go ahead and say pi 4 for pi, or pi 4 for pi over 4. That's what this is going to be, because it's going to add up to pi over 4. It's going to be equal to 0 to start with. Pretty bad approximation there, but hey, for I in range, you can make this a bit more understandable. For number in range. And then what we can do, just to show that we can, is that we can do something like 1 to 10 up by 2s, right? Print the number, go from 1 to 10, go up by 2s. And we get 1, 3, 5, 7, 9. And this goes to any arbitrary value that I want. Okay. One thing to note, though, is especially in idle, printing takes a long time. Like so. I can, if you're going up to a big number, sometimes it's better to just like print done, like so, and just simply not do anything over here. And let's see, we're going to need to do pi is equal. And for this one, I'll just simply, as a statement as a placeholder, I'm just going to put pi is equal to 0 again. We're going to need to edit what pi equal to 0 is since we're accumulating with it. But for right now, I'm just trying to make a point. Done. One of the things you cannot do is I cannot leave this for loop empty. It doesn't like that. It gets confused because it says, okay, you said there was going to be a tab with some code next. You said there was going to be not just a tab. This colon promises me that there's going to be a tab, some white space indentation with some code. I don't see any code. It doesn't. These are comments. So I don't see an indentation with code. So it's getting all upset there. So that's why I put in some line of code. Okay. And you can see that whereas it took a long time for me to do this for loop when I was printing out everything, it didn't take nearly as long when I was doing just a computation. 10,000. That's not what I need. 100,000. Let's go to 1 million, 10 million. Let's see how it does. Does it choke at all? A little bit. Choked a little bit, but as you can see, that would take a long time for it to finish with your printing. So again, if you've got these really big loops, print statement, you want to remove those print statements once it gets really big, because we need to, first off, it's going to just make it hard to see what's going on, but also it's going to make it take longer when you're testing. Print statements are useful for debugging, though. So we're going to keep this number small. Okay, so 1 to 10, 1 up to, but not including 10, going up by 2s, 1, 3, 5, 7. So now we need to add all these one at a time. We want these all to be added together. So we want basically to add 1 plus 3 plus 5 plus 7 plus 9, ... Make sense? Okay. So now, to do that, we use the accumulator pattern. We say pi4, our accumulator is equal to what current value is inside of our accumulator plus the value we want to add to it. So we can say, we can do something like, and so we can print that out, and nothing appears to change on our end because I didn't alter anything. You know, I mean, I didn't alter any of the print statements. It's a common thing to do, one of the more common things, because again, your human brain and your human eyes are very good at making sure that you stay alive, so that, you know, you avoid getting eaten by a wild animal, avoid, you know, cars, you know, suddenly see something in your peripheral vision. Very good at that stuff. Keeping track of code this isn't exactly what we were, you know, built for doing. But but the beautiful thing about the brain is that you can wire it however you want with plenty of practice. Okay. So what we can do is that we can now make our print statements more informative. Pi4 is going to be, so we can say print the current value of pi4, or we can print the value we're going to add to it, number, and we can print out what it's going to be afterwards. Pi4 plus num. Specifically, what we can do is let's go ahead and erase this. So let's go ahead and be a bit clear. We can add some text into there. So I'm printing out the current value before we add things, the value we're going to add, and then their resulting sum. And I can just make that clearer for us by saying what operation I'm actually doing. So I'm starting out with 0 in pi4, 1 for a value, sorry, 1 for the number we're adding, and that will give us 1. So we see that in the next line, we start with 1. The next number to add, right, it's 1, 3, 5, 7, 9. So 1 plus 3 is equal to 4. So we start 4 in the next one. Then we're adding the next value, which is 5. 4 plus 5 gets stored in pi4. So in the next value, we take pi4, add number, which is 7, and store that resulting sum, which is 16, in here, in pi4. Then we do 16 plus 9 to get 25. That's the value that we store in there. Done. Sum is pi is comma pi4. Be sure that when you do that, comma, you know, and then the variable, that the variable's outside the quotation marks. Okay. And again, we can just simply we can get this to go arbitrarily high. Just remember, the bigger it gets, the more you have to read, and the longer it's going to take to print out. Idle is great for beginners, but it's one big fault is that it does take a while to print out the print statement, a bit longer than other programming languages I found, but that's okay. It works just fine. I'm sorry, other IDEs, not programming languages. Okay, so we've got this first part going, 1 plus 3 plus 5. So now we need to do we have two more things we have to do. We need to turn this into adding fractions, or we have to turn this into an alternating sum. You know, +3 -5, sorry, 1 minus, let's see, actually, let me look it up. Always look up what you're doing. 1 - 3 + 5 - 1 + 9. So we have to turn it into the alternating sum, and we have to do the fraction thing. Which one do we want to do first? Doesn't matter which one we do first. So we can do the fraction first. So we want to turn this into 1 + 3 + 5. Sorry, from 1 + 3 + 5 + 7 to 1 + a third + a fifth + a 7. So one of the key thing, which is obvious once you rethink about it, to turning this into 1, 5, 7, and 9 is that 1 at the beginning is 1/1. So we don't actually have to edit number all that much. We can change its name though. In nadir. We can change it to denom for denominator, because denominator is long. Okay. And what we can do here is, rather than adding that number, which is 1, 3, 5, 7, 9, we can add 1 over that number. Just that once you see it, it's like, oh, right. And then just all I'm doing is replacing num with 1 over denominator. Which gets a bit messy because the fractions are kind of long. But we can see here 1 + a third + a fifth + a seventh + a 9 + an 11 + a 13th, and so on and so forth. And again, it gets messy because these are not nice, nice decimal fractions. They're the kind that a lot of them are irrational, and some are just repeating. Wait, no, they're all rational. What am I saying? They're all rational, but a lot of them are just, they don't encode nicely into decimal. Like, this one over here, this repeating fraction, I just saw it, 303030. Oh, yeah, why not this one? 027, 027, 027, 027, 027, 027, 027, because it rounds up at that point. There is something called the IEEE double precision floating specification, which describes how computers handle decimals. If you really want to get deep into the weeds, you can read that document, which goes into binary encoding. That's how it works. It works the exact same here. But suffice to say, there's just only so many significant figures that a computer will store for floating point numbers. Okay, but now I would say this is working. I mean, again, what we know is the one that's easy for us to add, which is 1 + a third + a fifth. A third is 0.33 and change, and a fifth is 0.2. 1, a 3, and a fifth. So that works, as far as we can tell. Okay. Now, going back to this, right? We've got our pi/4, where we've got our denominator, we've got our range, and now we've got our, well, it's kind of annoying. We've got to figure out how to flip. We've got to basically flip the sign. Minus, plus, minus, plus, minus. So it's every other one. Now, if we know how to do an if statement, this isn't too bad. We can just simply do that, except I only mentioned an if statement down there, and I don't want to get into that. So again, the key here is to recognize that basically that the positive numbers are multiplied by -1. So the positive numbers are multiplied by 1. The negative numbers are multiplied by -1. Make sense? So here, what we can do is that I'm going to create a variable called sign. It's equal to 1. Okay. And what I'm going to do is I'm going to do is I can basically say it's whenever we're going to do this, no. Now, what I'm going to do is that I'm going to replace sine times, I'm going to replace 1 over denominator with sine times 1 over denominator. Basically everywhere we see it. I don't need to put in, I don't think I need to put in any parentheses anywhere because of how I'm doing this with order of operations. Order of operations works almost completely the same as the ones you've been taught in school. I say almost completely the same because you typically don't get taught how to do modulo in school, and you typically don't have to worry about ands and ors, which have their own precedence. More on that another time. But the point being is that if you're curious, this assignment statement has the lowest precedence of all. It is defined to have the lowest precedence because you got to solve everything on the right side before you can do the assignment statement of storing things. That's what, so that has the lowest precedence, period. So here, this isn't going to change anything because, again, all I'm doing is multiplying the numbers by 1 at this point. Okay, and you can see that it's all the same. I'm going to shorten this to, again, 10. So it's still going to be messy, but not like a disaster, but not like a FEMA reclamation kind of thing, or not like a FEMA Superfund messy, you know? So now we got to get this alternating. So what we can do here is actually, I should pull this sign out because if I keep it sign at the beginning over here, if I keep declaring sign inside, it's going to change. It's going to always be 1 each time. If it's outside, I can change it over here each time I go through the loop. What do I mean by that? I can do sign is equal to, what I can do is I can say, here's our sign. And there's a couple different ways I can do this. There's lots of ways I can set this up. This is what I'm deciding. We do our operations with the current sign. And then when our operation is done, what I'm going to do is I'm going to say sign is equal to sign times -1 in order to flip the positive 1 to a -1, or the -1 to a positive 1. Make sense? And the computer is smart enough to realize, wait, that is a unary operator that you've got over here. A unary negative sign as opposed to a minus sign, right? They look the same. But the computer is always smart enough to figure out that when you put a negative in front of a number, you mean the negative number. It knows that you're not trying to do a weird operation called times minus or anything like that. It knows it's a -1. And so there we get 1 minus a third plus a fifth minus a seventh. There we go. So now what we can do is that we can bump this up to a ridiculous amount, 1,000, and we can run it, and we get our results saying done. Sum is 0.784.48. And remember, I said that pi over 4 is 0.7 and, it's 0.785 and change. So that's something like it, but we know pi better than we do pi over 4, so why make it hard for us? Done, sign is pi over 4, print pi approx, well, yeah, pi, and I'll just do the wavy sign over here, you understand. Approx equal to, and then we'll do pi 4, or 4 times pi 4, right? Because this is pi over 4. This value is pi over 4. I'm multiplying it by 4 to get rid of the over 4 bit. So now we'll get a value that looks like pi. 3.13, right? That looks like pi. Well, it turns out actually that adding in all the way to 1 over 999 doesn't really give you a good approximation of pi. In fact, if I go over to 1 over 10,000, sorry, 1 over 9,999, we get 3.141, and we get another digit. If I do it 10 more if I go up to 100,000. So another order of magnitude of approximation, I get 3.1415. And again, the next digit would be 9. Although interestingly enough, the next digit's correct, 2. Right? And then if I go over to 1,000,000 of these, 3.14159 as opposed to 2. So these things are pretty, it's interesting to see that we can do these like kind of approximations. Now, this may seem pretty nasty right here. This is pretty clunky and mathematical. And I know that a lot of you aren't into like doing the mathematical stuff. That's okay. This lecture is useful because I'm trying to show you one of the beautiful things about computer science, about programming, which is that once you get a bit under your belt, it lets you be lazy. In fact, we have mathematics has an entire series of classes devoted to this kind of laziness called numerical analysis, and they wouldn't describe it this way, but what they're saying is that differential equations are hard. These mathematical things are hard to solve. So let's not solve them. Instead, let's create an approximation algorithm, something like this that we just did, right? Something like this, but maybe for a differential equation or something like that, that's easy for our computer to solve. And then we do it, and yes, it's going to have some error because we need the more time, the more digits, the more figures we give on it, the less the error will be. But remember, your computer, it can only store so many digits so much. So if we do it enough times, the error is going to be smaller than this amount. So at that point, your estimation is exactly equal to the right answer. So who cares? Because you got the right answer, right? So it's pretty cool. So that's pretty useful. Now on to the non-math stuff. And here what I'm doing is that I'm turning this thing into a multi-line string, which is effectively acting as a multi-line comment, meaning that it's all commented out. Now I want to go back near the end for the last part of class before I ask you to do something else, which is I'll give you time to fill out a survey. Before we go to that, I want to talk a bit more about turtles and what we can do about this one. One of the things we can do with turtles, right, is we can, so let's go ahead and import turtle. Bob is equal to turtle.turtle with, okay. And what do we do here? So what we can do with Bob is that we can set up a color. Bob.color, I believe is the command. If I can type it correctly, geez. We can do stuff like this. Bob is equal to color red. And he turns red. Let's see, Bob dot set with, or set, what is it? I always have to reference things. It's fine if you do too. Doc, Python, turtle graphics, pen size. Yep, pen size or width. Pen size, and then, or let's see, size. There's turtle size, and then there is shape size. There we go. Turtle dot shape size is equal to 2. Let's go ahead and make them, because this is small, 3 and 3. And we can make them nice and big, right? There we go. Bob dot width is equal to 2, and that means what he draws is useful. But what I want to focus on here is the color. Okay, color is equal to red. So we can give it predefined colors like red, green, and shouty blue, which is no different than regular blue. So we've got different colors here that we can define. But this isn't all the colors, right? Certainly not. What we can do is actually we can declare a new color. Let me go ahead and simply, so this takes in, so I can do something like 0.2, let's see, I believe it's 0.2, 0.5, and 0.5. I could do something like that. And yeah, I can define a certain color. I can say, hey, set this value to 0. And I get a value. And that's a very deep purple. Let's go ahead and add some more. Let's go ahead and add some more red there. There we go. More of a funky purple. It's easier if I maybe move him a bit. Bob dot forward. Yeah, let's go forward 100 pixels on my computer. So we can define these colors, which is pretty cool. And what I'm doing here is that there's 2 color models. I'm using the one that's currently built in because that's less lines. But what it's saying is that these 3 numbers, these 3 floating point numbers, are between 0 and 1, and they represent the amount of color of one type of light. So the first one is red. It's 0 means no red. A 0 at the front means no red. A 1 would mean all of the red. And if I were to do half, it's like a bit of the red. And so our colors are red, green, and blue. Those are our colors. Red, green, and blue. And basically we just can add in just random bits of light into here to make, so we add some red, a little bit of green, and a whole lot of blue. And we get, again, this nice purple color over here. But what's fun and if I throw this in a for loop, right? Let's do for I in range 100. Or if I tell Bob to do this 100 times, he will. Bob dot move forward, because Bob is very well behaved turtle. Bob dot forward. Let's say 200. No, let's do 300. Then Bob dot right turn 90 degrees. We're not going to mess it up too much here. And I'll just shorten it for right now because I don't want to do this, right? He'll do this. Okay, and he'll just draw a circle and he'll keep drawing it until I want him to. And as I discussed last time, if I add in a bit over here, I can add in a bit of, an angle by just adding a 1, and it suddenly becomes like this. Alternatively, what I can do here is I can keep this, but I can do something like this: 300 plus 10 times I. Right, this value is going to keep increasing. And what I get over here is a spiral, because what I'm doing is I'm making this progressively bigger. Right? 300 plus 10 times I. So it starts out as 10 times 0, which is 0, then 10 times 1, which is 10. So it becomes move forward 310, then move forward 320, then move forward 350. And so we get this nice square spiral. If I were to make it a different shape, so if I wanted to make an 6-sided shape, 60 degrees, it works out the same kind of way. I can make myself a hexagonal spiral. Although made it a bit too big on the sides, that's okay. Let's go ahead and start out at 200. But now we can throw color into the mix, which I like. We can do, as we change, we can say, hey, as you're moving, so this goes up to 20. So let's see, we don't want to exceed 1 on any color. So let's see, we're going to add some more color, and it needs to be scaled appropriately. That's just requires some math to figure it out. So maybe, since we're doing this 20 times, go up to 0.2, no, 0.02. There we go. And then minus 0.02 times I. And so, again, what I was talking about with for loops is we can do these things of making shapes with minor alteration. And as you can see, it was hard to see at first when it started, but as you can see, our shape and its color changes from a purple to more of a yellow, just very gradually. It does it, but we can get these really cool effects. And now if we go back to what we were doing earlier, where we add in the bit of perturbation, a bit of a spin to the turtle, and we also do Bob dot, let's see, we can do Bob dot speed is equal to 10 so that we can see this fast. And we can see that we've got this angle that goes on, and let's go ahead and increase this to 100, and well, we'll crash if I do that, but that's okay. 100, so 1, and then we can just simply do, and we'll just move forward 200 times. We'll keep the distance it moves forward, and we're just going to change the angle. And we see that we get this very interesting, pattern. It's crashing because one of the values I put in for color went above what it liked. It specifically went above, this added up above 0.5. That's why. So, but we can see that basically it's fun. It is that there's a way we can draw these really complex geometrical patterns using color. It's certainly something to think about. Now, again, with the homework that's coming up, the lab that's coming up on Friday and Monday so lab 3, you don't need to use for loops. Now I'm going to dump this on the Discord channel so that that's easy to, hopefully it should be easy at that point to find. Oh, right. TAs are striking. Yeah, that's a thing. Basically, if the TAs aren't striking, they'll tell you if they're not coming to lab or not. If they're not coming to lab, I know for a fact that some of them are not striking. So, but if you didn't receive an email from them saying that if you haven't been told otherwise, your labs are going on as normal. Okay. But anyway, with regards to that, the last thing I want to do, and I'll stop sharing, is, oh wait, no, I still need to share, is so before class is done, you may have gotten an announcement last night, which was a follow-up to to the announcement announcement earlier. There's this research project I'm working on about mindsets and active learning and computing. So if you go to announcements, you'll also have received this as an email that I've got a survey as a research project. It's the same survey that got sent out earlier. The wording of the other one implied that it would take a half an hour to do the survey. That is not correct. It will take, at most, if you're extremely slow about it, a half an hour. It will take about 7 minutes. Because for reasons for doing these surveys, we have to say there's a maximal time, and that just got sent out in the first one. But it would be a great help for me if you were to fill out this survey. I will not be able to tell who fills out this survey. I'm not going to be able to tell who doesn't fill out this survey. All this is completely anonymous. So please fill out this survey. You can take the time to fill it out now. You can go home and fill it out later, but this will greatly help in a research project that I am actively doing. So, if you have the time, please stay behind and work on it. And class is dismissed otherwise. Again, it will take just about 7 minutes.